So we're going to do a couple of days now of factoring polynomials. We've learned the skill of dividing, which is what factoring is. If you think about even just factoring like a quadratic from grade 10, you did a lot of that in grade 10 and grade 11. You know, you're really breaking it up. Like if I take 12 and I factor it, 3 times 4, right? I'm just dividing. 12 divided by 4 gives me the 3. 3 and the 4 are my factors, right? So it's the same process, we're just dividing. In that case, we're looking for perfect factors, so no remainder, right? The skill of dividing polynomials that we did yesterday sometimes ended in a remainder. That's fine for that skill because we need to know how to divide in order to factor. But when we're factoring, you can't have a remainder. We want to have a properly, perfectly factored polynomial like we saw in grade 10 and 11 for quadratics. So that's where remainder theorem comes into play. So remainder theorem just says that if the function f of x is divided by x minus a, so that could be x minus 2, or it could be x plus 2, right? And then a is negative 2. The remainder is f at a. So what does that look like? Okay, let's take a look. For the function f at x equals 2x to the 4th plus 5x cubed minus 29x squared minus 38x plus 120, determine the remainder of each divisor. So for this one, my a would be negative 1. So if I want to know the remainder, I just calculate a at negative 1. Sorry, f at a, which is negative 1. So we're going to try, yes.
Why is a negative 1?
Because that's what remainder theorem says. So it's x plus 1 is what I'm dividing by, but it's x minus a. It's the same reason when you are solving a quadratic equation. Okay, so if I do something like this, x squared plus 7x plus 12 equals 0. And that factors to x plus 3, x plus 4 equals 0. So x equals negative 3 and x equals negative 4, right? It's the same reason. It's kind of the same reason why the shifts, the horizontal shifts, are backwards, right? All of those ideas, all those concepts are related. They're all basically the same thing. They're all results of the same mathematics. Okay, so you certainly flip the sign. You put that in. And we're going to streamline this process. In fact, most of the time you can probably just do it on your calculator. So negative 1 to the 4th is positive 1 times 2 is 2. Negative 1 to the 3rd is negative 1 times 5 is minus 5. Negative 1 squared is positive, so this is going to be minus 29, and then plus 38 plus 120. Use my calculator. I got 126. So my remainder is 126. This means if I did the division, if I divided x plus 1 into f at x, that's what I would have found as my remainder. That's what remainder theorem says. If all you need to know is the remainder, you can just find the value of the function at that point. Okay, so you can try the next one. A little bit harder with a 2 because you have to actually, like 2 to the 4 is 16, so you have to do some multiplication. Don't forget to change the sign, so it should be positive 2. right, that gives us 0. Therefore, x minus 2 is a factor because our remainder is 0. Okay, so factor theorem tells us that, in fact, exactly, if f at a is 0, then x minus a is a factor of f at x. And so this is an easy way of finding, an easier way at least, of finding a factor. So we can use, and then we can use that to divide and start actually factoring polynomials. Okay, so let's try this first one. So we're looking for a factor, and you know, you want to start with the easiest ones and then work up. So try 1, try -1, try 2, try -2, and so on. This is the same question as we just did above, so we already know that 1 and -1 don't work, but 2 works. So f at 2 is 0, means x minus 2 is a factor. And so we are going to go ahead and factor using synthetic division. Bring the 2 down, -4, subtract, -18, subtract, that's -11, 22, subtract, gives me -60, 120, and of course, we designed it this way. We designed it to have a remainder of 0. So if we didn't get a remainder of 0, we either made a mistake up here, or we made a mistake here. So it's better work out that way. Okay, so what does this mean? This means that f at x equals x minus 2 times 2x cubed plus 9x squared minus 11x minus 60. All right, now we're not done because we got to keep factoring. So we're going to let g at x equal this guy. And we have to find, we'll use remainder theorem, factor theorem to find a factor of that. So let's see. I see some multiples of 3 in there. I'm going to try 3, and I'm thinking, yeah, -3 might be the right way to go. So that'd be 2 times -8 plus 81, 9 times 9, minus, no, sorry, plus 33 minus 60. On second thought, it's going to be positive 3. So 2 times 27, I did that wrong anyway. 2 times -27, let's try that again. Plus 81, plus 33 minus 60. Yeah, 0. So that was -3. G at -3 equals 0. Therefore, x plus 3 is a factor. Now, we could use synthetic division again here, but we actually don't have to. So we're going to watch this little trick. So therefore, f at x equals our first factor that we found, our second factor that we found, and how do I figure out what goes here? Well, I take a look at what the outcome has to be. So 3 times something has to give me the -60. That part I know. So that's going to be 3 times -20 has to give me the -60. Similarly, x times something has to give me 2x cubed. So what's that have to be? Well, 2x squared. And then here's where, again, I use, this is very similar to just factoring a trinomial. We're just kind of using common sense, thinking about what we need to get working backwards using some common sense, some logic to figure this out. So what I'm going to do is I'm going to see that 3 times 2x squared would give me 6x squared. I have to get 9x squared. That's my result. So what has to be left? It's going to be x times something to give me what I add to 6x squared to give me 9x squared. So that's going to have to be plus 3x. So that the 3 times 2x squared gives me 6x squared, and the x times 3x gives me 3x squared, and I add those together to give me the 9x squared. And then I can check this. Let me get rid of all of this. I can check this with the x's. So negative 20x plus 9x gives me negative 11x. So same thing. Okay. So then that last guy there is probably factorable as well. And so it's going to be 2x and x. And it's probably 4 and 5. So let's see. Yeah, 2 times 4 and 5 times 1. And 2 times 4 is 8. So that's positive minus 5x. And that guy's done. Okay, so let's try this one more time. So I'm looking for something that gives me 0. I'm thinking it's either 1, negative 1, or look at all these multiples of 3. When I see a multiple of 3 like that, I'm thinking that 3 or negative 3, one or the other, is going to work. And again, you can use some, like if you start thinking about, well, if it's negative 3, this one will be positive, this one will be negative, negative, positive, negative. They kind of alternate. That looks good to me. If I made it positive, sometimes you can kind of use some educated guessing, but that's never a guarantee. So let's try 2 plus 5. It's not going to be positive 1, because look at all the stuff I'm subtracting and I'm not adding very much. But negative 1 will make them, this one will be positive, this one will be negative, this one will stay negative, this one will be positive, and this one will be negative, right? So I have a few of each, so it could be that. 2 minus 5 minus 15 plus 45 minus 27. Look at that. So f at negative 1 is 0, therefore x plus 1 is a factor. Like I said, I'm thinking maybe 3 as well, or negative 3, but we'll have to wait and see. So x plus 1, 2, 5, 15, 45, negative 45, sorry, negative 15, negative 27, 2, 3, negative 18, negative 18, so 45 minus negative 18 is negative 27, and the remainder 0, as was expected. Therefore, f of x equals x plus 1 times 2x cubed plus 3x squared minus 18x minus 27. Okay, so let g at x equal that guy. We'll find a factor here. So 1 didn't work before, it's not going to work now. If it wasn't a factor before, it won't be a factor now, that's for sure. So let's try, I'm going to jump to 3 and try 3. I'll try negative 3. So 2 times negative 27 plus 3 times 9, so that's 27 again, plus 18 times 3 minus 27. Oh, that worked. So that was negative 3 equals 0. Therefore, x plus 3 is a factor. So we've got, therefore, f at x equals x plus 1 from before times x plus 3, and we're going to do our little trick here. So x times something has to give me 2x cubed, so that's 2x squared, right? Just sort of working backwards. And 3 times something has to give me negative 27, so that's going to be negative 9. And then, again, I get 6x squared, but I need 3x squared. So 6x squared minus 9x squared, right? There's that. So 6x squared minus 9x squared gives me, no, sorry, it's positive 3x. 6x squared minus 3x squared. I was trying to make it negative. So 6x squared minus 3x squared gives me the 3x squared. And let's check that with the other one. So that would be negative 9x minus another 9x gives me negative 18x. So that works. And then factor this last quadratic. Two x and something. Oh, and x. And looks like it's going to be 3 and 3. So that's going to be negative 6x plus 3x gives me negative 3x, and we're done. And when you're done, you can look and see what the other factors were. So negative 3 would have worked as well. There's another 3. You can see why there are so many factors of 3 because there's a lot of 3's in there. And sometimes, you made a mistake or whatever, you missed one. So let's say you try negative 1, you try 1, they don't work. But then when you finish factoring, you actually see it in there. So you made a mistake. It's just good little thing to go back and reflect on. Think about